This substrate is safe for transport, even over 24-hour period, and helps in the first stage of methane fermentation. According to research of automatic methane potential test system, our substrate has almost same biogas potential as traditional substrates from agri-food. Based on the information available in the literature and our conducted research, we have developed a complete technological layout for the plant, including unpacking and sterilization, based on individual devices available on the market. We can offer just a substrate preparation facility or the entire biogas plant, including selecting the process parameters. Our solution is technologically simple and what every businessman wants: cheap. Elaboration of the positive environmental impact. The use of energy crops like maize as substrate in biogas plants is expanding, leading to concerns about the negative impact on traditional crops and biodiversity. Minimal use of meat waste in biogas plants due to safety reasons can be improved through innovative treatment and sterilization process. As we all know, biogas can be used to produce hydrogen, which can be used, for example, to steel production. Also, thanks to biogas, we can produce methane, or we can use it to produce electricity and heat in thermal plants. Okay, right now we know what we can do from biogas, but what benefits will biogas bring for environment? If there will be any positive impact? The answer is, of course, yes. Our project reduces food waste with regard to out-of-date waste, especially of animal origin. Also, reduces thermal treatment of waste, which is not in the line with the waste hierarchy. Reducing monocultures and increasing biodiversity, possibility of producing final product such as biomethane or hydrogen, or only substrates for biogas plants with an extended shelf, which we can achieve thanks to sterilization. And last but not least, we can produce green energy. Economic viability. On the basis of our solution, there can be created clusters that brings together supermarkets, food producers, and already existing biogas plants. We have European funds that can be obtained for this, and also collection agreements that can be signed with industrial plants, such as chemical, refinery, metallurgical industries. Financial participation from large-scale retail chain in building waste collection and thermal treatment networks can lead to cost savings for both waste management and energy consumption. Green certification can positively impact ESG reporting. European policies offer support through various projects and funding opportunities for biogas plants. By using UV sterilization process, the product becomes safe enough to be sold to all methane fermentation plants. Without this process, the product would only be suitable for biogas plants that have a pasteurization line for third category. It means raw materials. This UV treatment gives an opportunity to be used more widely, and we can be sure that all standards are met. This also simplifies the process for plants that might not have the equipment for another type of pasteurization, making the product more universal and available. By using agglomerates in tanks, there are fewer operational issues, less damage to equipment, and reduced need for electricity, and of course, lower service cost. We are sure that our idea is a solution for markets, biogas plants, society, and above all, for the environment. This project is technically and structurally complete, based on the economics of the entire project. It positively impacts the environment in every aspect and meets all European guidelines. By implementing our idea, we are able to base the biogas plant feedstock mainly on expired meat products, which can soon also power your home with green energy. Right now, thank you so much for your attention, And now we are waiting for your questions.
Well, thank you, Philip. That was excellent and very well timed. You can stop sharing from my point of view. Thank you very much. 9 seconds left. You practice a lot, didn't you?
That was first time.
Then you're a master. Okay, open for questions. Manfred, please go ahead. You're mute, Manfred. You're mute.
Yeah, thank you for this, for presenting this clever idea to make something out of food waste. My question is about the source of the food waste of this meat. This waste material is produced at the consumer level, at the retail level, at other levels in the value chain. From which partners will you source your material?
Our idea was taking from the supermarkets, from stores, out-of-date products. So it's not from customers directly, but from the businessmen, from market, and etc.
Thank you.
Lena?
Excellent presentation. I'm really impressed, and good focus on the food waste. I have a question, and that is you are claiming you're reducing food waste. To me, it sounds like you are valorizing the food waste and not reducing the amount of food wasted.
As we said, we can do biogas plants working just on feedstock from from meat products, but it can be also a substrate to be adding to another feedstocks. So it's not necessary working just on the meat products, right? We can just add it to another feedstock. So we don't wanna make problem bigger, but we wanna find a solution with, let's say, using less thermally process and use it to transport this energy to green energy, to biogas, and then, of course, hydrogen. For example, hydrogen.
Okay, Kevin.
Yeah, thanks very much. I want to echo what the other judges have said. It's really excellent presentation, very clear what your goals are. I wanted to ask you about two things. One is, have you considered seasonal variations or the variations in general in your feedstock and how you would control that?
Philip, did you get it? Yeah.
I'm so sorry. Can you repeat first question?
No problem. How do you control for variations in your feedstock that is going to go into the anaerobic digester? So, for example, at Christmas time, you'll probably see more turkey meat. And then maybe at Easter, you get more lamb meat. And also then you may get some festivals over the summer. You get different types of food. So how do you control for that variation to make sure that your anaerobic digester is functioning optimally all year round?
Okay, thank you for repeating. After our researches, we want to use sterilization process to by UV method, and that's the idea of that's why we can use, for example, lamb meat, for example, turkey, as you said, or chicken mixed together, because after the sterilization, our feedstock will have same chemical and physical potential. It will be stability.
Okay.
Thank you.
I haven't heard Sophia before, Lena, so I give her the floor.
Thank you. Congratulations. I really enjoy your presentation and your work. I just have a small question. Do you have any research that indicates that if the efficiency of your sterilization, it will be the same expected as the most traditional issues, although they are not the same raw materials? But if we will expect to have here some efficiency differences that need to be adjusted? Thank you.
Yes, we made research by using UV sterilization by radiant method and thermal processing. So we chose UV sterilization because it's the most, I would say, friendly for it's more friendly for environment than thermal processing, and it's cheaper than radiant method. And thanks to that, we don't lose biogas producing potential, and that's why of course it's maybe we're gonna need more time for making the UV sterilization process. It means like the time is just longer, you know, with processing in that way, using this type of sterilization. So yeah, the process will be longer, but in the end, it will be cheaper and more friendly for environment.
Lene?
I would like to ask if you have considered to valorize more part of the than just utilizing the energy content of the biomass. For instance, in most biogas, there is a very valuable digestate residue with minerals which can be used for actually getting as a soil improver. That's one part. And the other part is that, have you considered whether the biogas with only meat, with all this protein, and no fibers at all, is giving the best biogas operation? Most biogas, as I'm informed, have a mixture.
Mm-hmm. You're mute, Philip.
So sorry. We considered using biogas for hydrogen and for producing methane. Also, it's gonna it's good for biodiversity because we quitting the monocultures. So as you said, the soil will be we're gonna have it's gonna get chance to renew, right? It has time. So yeah, we especially focus on biogas and from biogas to hydrogen and methane. So this is our main clue. Yeah.
But adding to Lene's question, you have, from the chemical perspective, you have nitrogen in an active form. Actually, in one of the highest forms we can imagine, included in protein. And we should keep it there. Like everybody is working on getting rid of NOx and ammonia, we shouldn't do that. We should keep NOx and ammonia, let alone protein, and reintroduce it in the feed chain. Because getting it done in the human chain, well, it's overdate, so that wouldn't possibly work. But having all those complex molecules there, which are from the trophical environmental pollution, highest on the ladder, I don't think, I'm sure they are, to getting only the hydrogen atom there and make hydrogen gas for transport. I cannot imagine that is economically worthwhile. But please help me out here.
We're trying to reach just a substrate for biogas, so that's why we choose this UV sterilization. It's much more cheaper than thermal processing, and I agree with I agree with you, but we still believe that our project is complete and financial good for also businesses, but also for biogas plants.
Okay, thanks, Philip. That was not my phone ringing that somebody called me, but the phone with the alarm. So we have to stop here. Thanks a lot. Yeah, well, a normal audience would have an applause now, but digitally it doesn't make sense. So we move to the second team, which is Lithuania. I hope everyone's ready there. Oh, Kevin applauded.
Hello.
Thank you, Kevin.
Hello, we are here.
Please go ahead.
Wait a second, we'll upload our presentation. Okay, can you see the presentation?
Yeah, we can. Hello,
Yep.
everyone. We are a nanobio spray team representing Lithuania in BISC competition this year. We are glad to be part of this competition for this year. Photoactive nanoparticles electrospray, a novel way to combat microbial contamination. Meet our team, Dominikas, me, Yaniv, and Gabia. We are master students at Venice University under the guidance of Dr. Vanessa. Microbial contamination, who hasn't heard about it? Microorganisms, actually, it's everywhere, in our kitchen, in our houses, transport, public transport, hospital, healthcare, it's everywhere. But why we should share? Why should we care? Because actually in Europe annually, the microbial contamination causes close to 42,000 deaths annually, and in the global world, like close to 20,000 deaths globally. And this is according to the CDC and to the WHO organization, which searched in the hospitals and food industries and farms. Which also the cost reach to $23 billion in Europe, and more than $200 billion worldwide, like globally. So this contamination caused by various microorganisms, for example, E. coli, Enterococcus, and Pseudomonas, Salmonella, and more. To overcome this contamination, traditional today, we use different chemical agents like alcohol, ammonium, phenolic, sporicides. But these agents come with their own risks, for example, such as health risks, environmental impact, also develop of the resistance of microorganisms, waste, and resources use. Our innovative solution uses fullerene nanoparticles, which have demonstrated as antimicrobial properties, which offer a safer, eco-friendly alternative that it's more effective at killing microorganisms such as fungi, bacteria, viruses. And further to the antimicrobial properties, also our fullerene nanoparticles is stable in different temperatures and different condition in the hospital surfaces everywhere. Also, it's non-toxic for the human cells, reduce the environmental impact, and also energy efficiency, which is rely in the light, white light, which my teammate will explain it later, Gabia.
Gabia, we can't hear you.
You are mute.
Sorry. So that's why we thought about using fullerene, a unique carbon structure. However, it faces the problem of hydrophobicity. So to solve it, we attach 5-aminolevulinic acid. And then we use chitosan to self-assemble the complex. And the biopolymer chitosan not only stabilizes the fullerene, but also adds extra antimicrobial properties. In this slide, you can see the illustration, which shows the process of how our antimicrobial coating is applied and how it works. So first, we prepare a solution of nanoparticles, which is then injected into an electrospray device. And this device creates a fine mist of these nanoparticles. And they evenly coat the surface. And once the coated surface is exposed to visible light, the complex produces reactive oxygen species, which are highly effective in disrupting microorganisms in different pathways. So here you can actually see the prototype of electrospray device, and it uses high voltage to atomize these nanoparticles solution into this fine mist, which is, as I said, evenly deposited on surface. And this method ensures a uniform, controlled application, making this process even adaptable for different surface types. And our approach is both innovative and sustainable because first, we are thinking to use chitosan derived from food waste, so like shrimp or crab shells, to create this eco-friendly coating. And the electrospray method allows precise control over coating thickness and coverage. Optimizing this antimicrobial efficacy and making it ideal for scalable production across various surfaces. And this nanobiospray technology can be applied to a variety of critical surfaces in hospitals, ensuring they remain free from these harmful microorganisms. So, for instance, high-touch areas like door handles, bed rails, and medical equipment can be coated. And additionally, surfaces in operating rooms, patients' rooms, and maybe even waiting areas can benefit from this coating too, providing an extra layer of protection in environments where cleanliness is vital. So our project delivers a novel approach to combating microbial contamination using photoactive nanoparticles applied with electrospray device. And these nanoparticles generate raws under visible light, effectively killing a wide range of microorganisms. And the electrospray ensures uniform surface coverage, reducing the need for these harsh chemical disinfectants and providing, of course, long-lasting protection. And this method is adaptable to various surfaces, making it ideal for enhancing infection control across various environments.
Okay, so let's now move on to the business part. So in our SWOT analysis, we identified our strengths as innovative technology, broad applicability and sustainability, while our weaknesses include high initial costs and the need for market education. Opportunities lie in the growing demand for hygiene solutions and market expansion, while threats include the competitive landscape and potential regulatory changes. One of the core principles of the Fullerene model of economics is sustainability. This means that economic systems should be designed in a way that minimizes waste and maximizes efficiency. This can be achieved through the use of renewable resources, the reduction of carbon emissions, and the implementations of sustainable practices in all aspects of the economic activity. Another key aspect of the Fullerene model of economics is the role of technology. Technology is seen as a key driver of economic growth as it enables us to do more with less. This means that we can produce more goods and services using fewer resources, which is essential for long-term sustainability. This model also emphasizes the need for collaboration between different stakeholders in the economy. This includes businesses, governments, and communities. By working together, these stakeholders can create a more sustainable and efficient economic system that benefits everyone. Finally, the Fullerene model of economics promotes the idea of a circular economy. This means that resources are kept in use for as long as possible and waste is minimized. This is achieved through practices such as recycling, reusing, and repurposing materials. Here we can see how much hospitals, farms, and food industries spend on disinfectants. Looking at all three of these institutions, we can see that average cost a liter ranges from 2 to 10 euros, while annual usage of these disinfectants range from 2,000 to 20,000 liters a year. This brings us to total cost ranging from 2,000 to 200,000 euros a year. Not to mention that most of the disinfectants are environmentally unfriendly and are not sustainable. Now let's see how much our product will cost. So first comes the material costs, which will include fullerene, which goes approximately from 200 to 300 euros per gram, then 5-amino-levulinic acid, which will cost from 500 to 1000 euros per kilogram, and chitosan, which costs around 25 euros per kilogram, but by collaborating with fishing industries, we could receive it for free. Next comes the production and the formulation of costs. Including synthesis, formulation, and quality control, it will cost from 10 to 50 euros per liter of our spray solution.
You passed the 10 minutes.
The last pass labor for application will cost from 10 to 20 euros, depending on the region. Finally, assuming we'll apply our spray once a year, it will cost from 3 to 8 euros per square meter. So annual cost estimation, if the facility is the size of 100 square meters, which is the average hospital area, it will cost from 300 to 800 euros. This cost is 10 times lower than using current disinfectants to cover the same area in either hospitals, farms, or food industry. Thank you.
Okay, thank you. That was a very clear statement with a key message. Please stay away from hospitals, if you ask me. But nice presentation. Can you stop sharing, please? We have questions from Simona.
Hi, thanks a lot for the presentation. I have a few questions. Can you hear me properly?
Yep.
Okay. Do you have already a prototype in place? So do you have already tested this innovation?
No, this is just an idea, but it is like covered by the literature that we have today. So in theory, it should work.
I can add also that we did in Vilnius in Lithuania a survey, which we asked if people in private companies like Thermo Fisher and the university, Lab University and hospitals, if they could use it. And they say if it's the idea is acceptable, and they say the survey was like very, very positive responses.
This is a good point. But technically speaking, I was thinking, are you sure about the possibility and the feasibility of spraying this kind of molecules, and which can be the hardest in that direction? And on the other side, since it is a derivative of the fullerene, do you have any reference about the biodegradation, the final biodegradation of these compounds?
Well, currently in the laboratory, the fullerene complex was tested and it works fine against the microorganisms, as we told you before. And what was the second part of the question?
Degradability.
Oh, degradability. So degradability was not tested yet. because it takes time for this complex to degrade, which is why it is so useful, because you don't have to spray like daily. You can spray it, I don't know, once a week, once 2 weeks, and it will stay. And yeah, if you are asking about the degradability, it was not tested yet.
Okay.
Yeah, my question was, probably it would be nice if you follow up with this innovation, to think about inserting also biodegradability test in order to make sure that how long these molecules are lasting, for both reasons. You have to find the balance between having there in your surface, but on the other side that they are not impacting for a long time.
Yeah.
Okay.
Thanks a lot anyway.
Well,
Okay, thank you. Manfred, go ahead, please.
Okay.
Well, my question was also about degradability. This has been answered already. The other question is about circular economy. You claimed advantages, benefits for the circular economy. What is the advantage?
Any of you are mute.
I say that related to the previous question, because as a Gabia explain it, it's with Ketozan, it's make it is more stable, so it's protected. That's why we combine the Ketozan with the fullerene for your question. And the other one, I couldn't hear the second question. If you can repeat it, please.
This was also only the question for the circular economy, what the circular part is. And you responded that the Chitosan is your component for the circular economy. So the question is answered. Thank you very much.
All right, Sophia.
Thank you for your nice presentation. And your work is within the theme of my PhD, so I really enjoy it. I have a question related to the operation time. You say that your solution can diminish, can affect bacteria and fungus, but we have different bacteria. For example, in hospitals, the bacteria are quite different from the usual other places, and we need sometimes for the operation, for the ROS to be effective. Do you test it those times? Do you know how what is the average time that the code needs to be in place before being functional, before it can be used to other to its objective? I'm not sure if you understand my question.
Oh, well, which one of you dares?
It's like, do you mean how long we need to turn on the electrospray before?
Yes, you need to disinfect something, right, in a hospital. You need to put the spray.
Actually, it's
and you need to wait some time to achieve your efficiency of the method. How long do you need to wait? Because we have different types of bacteria. The bacteria does not have all the same mechanisms. They don't have the same codes. So we need different times of operation times to be effective in different types of bacteria, or else we'll be removing the not so resistant bacteria, but leaving the ones that are more resistant. So do you test any different times?
It's like, as Gabia said before, our idea is like working on different different parts of the back. Like it's not specifically specific for one part, like as the antibiotic or other related antimicrobial components. According to like how, if we tested, like we haven't tested yet. It's like or Gabi, want to add something?
Okay.
Okay,
And I
We
can
have
say
two more
that-
questions. We have two more questions and we lack time. So Lene, go ahead.
I would really enjoying what you're presenting. It's very innovative and it's addressing a serious problem. I have a question about toxicity for man. I mean, if it's also toxic on man. Most of the people, most of the products which are active against fungi are also toxic for people. And I wonder, you would say here in your presentation that there are many different pathways or several pathways. It is destroying the microbes, but also you also mentioned in the application in your writing that it is destroying the cell membrane. Could you inform me about a bit, just in 1 or 2 sentences, about the mode of action?
Okay, so this product was tested in vitro in different types of 9F cells, so it is not dangerous for humans or human cells. And yeah, I don't know if I answered your question, and I just really want to get back to Sophia's question because I remember the answer. So the answer is minimum 15 minutes for it to completely work. Yeah, thank you.
So you tried against
Yes.
animal cells?
Yeah.
You did?
Yeah.
And what was the mode of action? I mean, is it destroying the cell membrane?
No, it is not destroying the cell membrane.
Okay.
Okay. Final, Kevin, very short, please.
Sure, yeah. Thanks very much. Yeah, very interesting talk. And as Lena said, very innovative, really interesting. I'm going to ask 2 questions. One is the throughput of the electrospray. How much product can you get through per minute, per hour? How long does it take, do you envisage, does it take to spray? Anybody? I don't hear anybody.
Depends on the size of the surface, I guess. So you can regulate how much you want it to spray, how not long, but wide, and how intensively. So I don't know if I answer your question.
Sure, that's fine. Yeah, it would be good. It would be good to know. I know you say it takes 15 minutes for it to act, but how long does it actually take you to spray a surface? Would be good to know because that's operational time that has a certain cost.
Not long.
All right, Jens, we passed the 10, so I have to stop you here.
Okay.
Sorry about that. It's just fair to the other teams.
Yeah,
really.
Sure. Thanks very much.
Thanks a lot. Very lively discussion, and we move forward to the Slovenia team, which is the last one for the break. Yes. Slovenia, are you there?
We are. Yes, we are.
Good.
Hi.
And the PowerPoint is on. Go ahead.
Yeah. Yeah. Dear audience, dear jury, welcome to our presentation. We'll present you the development of a bio-based material for the production of drinking water using evaporation technology. Our team's name is Evapotricity, and we come from Slovenia. Our team consists of 3 members, Max Brus, Matic Jančar, and me, Vit Rozman. And in today's presentation, we will take you through the introduction, technical aspect of the innovation, environmental impact, and economics of our idea. Okay, let's dive into it. We don't want to present the problem bigger than it is, but the predictions for drinking water availability are alarming. Right now, there is 26% of population without access to water, to safely managed water. And this percentage is increasing every year. And in just about 25 years or so, 2/3 of the population might have drinking water shortage due to climate changes. And as you can see on this graph, only 3% of the Earth's water is fresh, and a large part of those 3% is non-potable as well. Although the rest, 97%, is salt water, there are some possibilities of exploiting this resource with our evaporation system. So we have developed an evaporator made of renewable materials. Those are lignocellulose nanofibers. And it produces potable water using accelerated evaporation. our design can produce up to 6.3 kilograms of potable water per square meter daily. And the advantage is that the evaporator is simplified production process using renewable materials with also additional possibility of creating electricity. And now I'm passing a word to Matits that will explain the technical aspect of the innovation. There you go.
Okay, thank you, Vid. So yeah, let's put our evaporator into a slightly broader context, because we have also developed an evaporation module that will allow us to actually capture the water vapor produced. And you can see it here as a cross-section diagram. So the way this thing operates is fairly simple. You have a reservoir of non-potable water at the bottom, and then these evaporated discs that you can see as black rectangles are floating on top of it. And then when sun rays hit them, they heat them up, and that creates water vapor. And this vapor we can then intercept under a transparent dome, where it again condenses and then drips to the side into a collection channel. As you can see, the system is entirely solar operated, doesn't require any additional outside energy source, so that is great. Now on to the next slide. Let's have a look at the production of the evaporated discs themselves. I would like to state that there's only 4 ingredients in the discs. First of all, it's lignocellulose nanofibers, which is basically disintegrated wood. Secondly, polyvinyl alcohol, then citric acid, and these 2 components help with strengthening the material and stabilizing it. And then fourthly, there is the charcoal powder for dyeing it black. And the way the thing is done and produced, we start with lignocellulose nanofiber solution, which takes a gelatinous form, and that you can see in picture A. Then we add the polyvinyl alcohol and citric acid, and we mix it thoroughly. Then also add charcoal powder, mix it again, homogenize the thing. So we end up with a paste-like substance that we put into a petri dish, and then the whole thing in step F gets thrown into liquid nitrogen. And this freezing creates the formation of ice crystals along the thickness of the evaporated discs. And then in the next step, that's step G, we remove all of the water out of the system with freeze drying, and we end up with an aerogel, essentially. And this aerogel has along its thickness holes, essentially really tiny pores left from ice crystals that formed beforehand. So this promotes increased capillary action and also faster evaporation rates. And in the bottom row, you can see a simplified version of the evaporation module that I explained to you on the previous slide. So next slide, please. Let's also look at some technical benefits of our innovation. First of all, is a simpler single layer construction compared to some other similar things. Then secondly, we're using LCNF instead of cellulose nanofibers. So lignocellulose nanofibers are essentially a simpler product that requires 1 step of refinement less. So that saves us energy and also costs. And then thirdly, we're using simple charcoal powder to colorize the surface of these evaporated discs black. And that, as I mentioned, increases infrared light absorption and also speeds up heat accumulation in the discs, and therefore also speeds up the evaporation. And lastly, there exists potential for production of electricity, and that comes into play when we're filtering salt water, because a flow of ions gets formed between the bottom and the top surface, and a small current gets induced that we can then theoretically intercept. And now I pass my word on to Max, who will explain some environmental aspects of the innovation. Thank you.
Wow, thank you, Matthijs, for such a wonderful explanation. Now I would like to point your attention to the comparison with the current systems. The most widespread way of water desalination is reverse osmosis. While it is a well-developed and efficient method, the problem is that the membranes for filtration are difficult to produce, and the system is quite complex. So on the other hand, our product on the next slide would not require electricity to function, but instead would rely on solar thermal energy. Our system is therefore much simpler, it is less prone to failure, and it is easy to maintain. The possibility of electricity production is an added benefit. This could mean that with further research and industrialization, an evaporator optimized for electricity production could be developed. We also want to stress that the evaporator is bio-based. Lignocellulose nanofibers and charcoal powder are both produced from wood, which is a sustainable resource. Citric acid is obtained from citrus fruits, such as lemons, while polyvinyl alcohol is not usually bio-based. It can be produced from bio-based sources. It is, however, fully biodegradable. Now, another advantage on the next slide of our evaporators is the fact that they are an aerogel, which means that they have a really low density. Because of this, relatively low amounts of material are required to produce them. For example, 1 kilogram of raw material can be used to produce enough evaporators to support nearly 3 people with drinking water. Or if we look at it in a different way, a peach tree, which would otherwise be cut down into firewood, could be used to produce enough evaporators to support nearly 10,000 people. And now if we look at the business side of things, on the next slide, the important advantage over the competition is that our system uses a bio-based material to produce drinking water. This leads to a sustainable use of wood in an innovative way. Weaknesses may arise from developmental costs and potential market limitations. Unexpected competition and unforeseen technical challenges might also arise, but we plan to fight this with a robust subscription-based model, which would help fuel the research. Opportunities, on the other hand, include demand for sustainable products and solutions, potential partnerships with other companies, and governmental subsidies. Now, on the next slide, I would like to point your attention to the current market trends. The nanocellulose market and the desalination market, both of them show significant expected growth, 24% and 7.5% respectively annually. The main material, lignocellulose nanofibers, fall into the first category, while the evaporator module falls into the second category. And on the next slide, I would like to look at what we have done. Since our national competition, we haven't just sat idly by, but we managed to produce prototypes and conduct trials for our idea. You can see the results of our experiment in the graph. The blue bars represent the produced water with our evaporator module, and the gray bar presents just regular evaporation. We were able to produce nearly 3 times as much water using our idea, and using our sustainable formulation, we were able to produce evaporators that produce 6.3 kilograms of up to 6.3 kilograms of drinking water per square meter daily. So, dear jury and dear audience, what we have presented to you today is not just an idea. We have put it into practice, and it has shown promising results. With further support from BISC-E, imagine what we could achieve. Thank you for your attention, and we will gladly answer any of your questions.
Wow, thank you. That was excellent. Please stop sharing. I see a question already from Sophia.
Thank you. Congratulations on your work. I really enjoy your work and your presentation. It was very clear to me. I just have a question. Maybe you talk about it. What is the lifetime of the evaporation discs, and what is the disposal that you're thought about?
Well, the lifetime of the discs, so for example, how many cycles this can make of evaporation, is that the question, sort of, if I understand correctly?
Yes.
Well, currently we've only tested this for 3 consecutive days, so we cannot comment on a longer term experiment. We haven't done such a thing. But due to the fact that most of the components are biodegradable, the end of life shouldn't be problematic. They could be just so put into a compost and degrade.
But well, I had a similar question, like, you know, you say it will last for 10 years, but that can't be true because there will be a lot of fouling, so to speak. But you haven't got a clue on how much. Okay, Manfred.
Well, congratulations. You address a big market and a real need of drinking water. I understand that the drinking water is, it's a demineralized water, that the water is condensing at the wall of the dome. This depends on the temperature of the wall. So my question is, does your system work in all climate zones the same? And especially, does it work in warmer climate zones where the need for the drinking water is really?
Yes.
Yes.
Go ahead, Matthijs.
Thank you. Yeah, of course, we haven't tested it in any specifically harsh climate, but we suppose that actually additional sunlight, which is more common in areas with drinking water problems, would be only beneficial because that would speed up the evaporation process. And as for the condensation, we assume that it will still function fine and accumulate enough water vapor because it does, let's say very simply, it does fog up really well and it does start to condense and drip to the side in any case.
Okay. Kevin? Oh, sorry, Simona was first.
Yeah, it's okay. So not a technical question. You mentioned that you have a small market as a weakness. I was wondering who will be your direct client here? Are you thinking about governments or?
In this case, I think it could be both, actually. It could be larger buyers and also people that just want a single unit of the system. For instance, someone that wants to be self-sufficient and not rely on any existing systems or infrastructure. But it can also be scaled up fairly well, we believe. Of course, we haven't tested it yet, but theoretically speaking, it does allow for proper scaling. You know, you could just put on a bigger dome, and we also did some calculations. You could actually make a system that's not just one evaporator discs, but many of them, hundreds of them, under a bigger dome, and then that can in turn supply many people at once, produce enough drinking water for probably whole communities.
So mainly you are competing with the osmosis-based system. This is the idea.
Yes, because that is somehow likely the most commonly used system for water desalination.
Okay, thanks. And also congratulations for the pitch. It was nice and it was really business-minded.
Thank you.
Kevin?
Sure, thanks very much, Keith. Yeah, really interesting talk again. The standard is incredibly high, so well done. Can I ask you about the environmental impact of the manufacturing process? Because you didn't really present, and maybe I would have liked to seen maybe a carbon footprint, because I see things in there that worry me a little, like freeze drying and liquid nitrogen. These are expensive, energy-wise costly. Yeah? So can you talk about that maybe?
Okay, yeah, let me try to tackle this. So the thing is that we haven't specifically calculated the carbon footprint of the thing. We kind of focused more on the cost aspect of the thing, and that we have calculated for a larger scale. But yeah, I have to agree in this case. Yes, specifically freeze drying is somewhat energy consuming. But on the other hand, we also have to consider that once we go on a larger scale, we have a big industrial freeze dryer that then can simultaneously produce hundreds of these discs at once. So we have one cycle only, and then it becomes more and more effective. And essentially, it just gets better with larger scale.
Very good, thanks very much. And Keith, just to Rob, another question. Maybe you should collaborate with the previous speakers to prevent biofilm formation on your on the surface of your dome, because I imagine that you might get some biofilm formation. So it's something that you could collaborate. Thanks very much.
Exactly.
Just spray it everywhere. Manfred, please.
Well, the system does not produce only water. It produces also fouling films, we heard it, and salt. So what are you doing with the salt? Is it a waste? And if it's a waste, how do you manage it?
Okay, let me try to tackle that as well. So yeah, we have put some thought into the fact that we will accumulate some salt on the evaporated discs. And for now, we haven't yet considered it as a usable side product, which certainly is an interesting idea that we have to keep in mind. But what we thought about is just first of all, remove the salt when the evaporated disc gets saturated. Use some of the water that you have just produced to basically wash it out, because we believe that simply cleaning them like that would work and they could be then reused again. And as for the salt, I thank you for the idea, because I think, yes, there is potential to actually maybe collect it and even use it.
Okay. I found two prices in your technical file, which is 3,933, which I thought was pretty much expensive, and I found 1,161. So do you have some insight in on how you actually come to a cost price of the thing and what your profit would be per square meter or per anything?
I think we have to mention a number that may be more that you can more easily imagine and compare to other things, and that is basically the cost of water per liter that you could produce with our system. And that, if I believe correctly, if I remember, is about 19 cents per liter of water.
Yeah,
so that is maybe
cheaper,
more kind of comparable.
All
and
right.
as for the price of the system itself, we calculated it from all the production costs down. We made a theoretical model of basically a small, let's say, factory that could produce these evaporation modules on a slightly larger scale and as larger modules themselves. And then from that on, we then calculated from the machinery, from the materials.
Okay, so and what's the price then? Was it the 1161 or the 3,933?
1161, I believe. Yes.
And that would be for 1 square meter, or?
That would be for one evaporation module that would suffice for one person. It would actually, produce enough water for one person for each day, for as long as you have sun shining, essentially.
So way over €1,000 for some
yes.
plastic with a disc in it. Come on, you can be serious.
Yes, but on the other hand, we believe that such a system could last you a long time. It may need replacement of the discs here and there, but on the other hand, the system itself will not be a one-time use thing. Of course, it will last you.
All right. Thank
many
you.
years.
Thank you. Any other members of the jury? And we have 1 minute left. So if there is somebody from the audience, a colleague, student, you could ask a question as well. Just raise your hand digitally. This is only for the very brave, I presume. It's the same experience every year. Yeah, Lena. No, you're not a student, but okay, come on in.
Yep. I took some time out to the student to come up. Otherwise, I have to say, I mean, I'm worried in the same thing about the price. But please, I would advise that you try to see for the customer who really want to pay a high price. That could be a kind of emergency or a camping gear, or I mean, so it is a survival. So you are suddenly out in not just common commodities.
Oh yes, I agree with that. On one hand, that is a potential market, and certainly our clients may be these. On the other hand, our ideal goal would be to make it as cheap as possible and also make it available to the people that really need it and can't actually afford it. That would be the perfect goal.
Thank you, guys. Excellent presentation, very well response to the questions. So we have a break now, and we will start again at 10:40. So go get coffee or do anything else you wanted to do.
Okay, thank you.
Thank you.
Thanks.
Well, slowly approaching. You were mute, Lena.
Punctually.
Ah, very good. Mes amis de France, vous êtes là?
Good morning, everyone. Can you hear us?
Yes, we can hear you.
Good morning.
Good morning.
Bonjour. You can start if you want.
Bonjour.
Let us know if you can see the screen, please.
You can see it, put it on. Yeah, exactly. All right, go ahead.
Bonjour. We are the biosurfers, and this is our bio-based solution for biosurfactant production.
Do you use soap? Have you ever eaten an apple? Of course. These products are part of our everyday lives. But have you ever thought about the impact their production has on our planet? Some ingredients used to manufacture them, like surfactants and pesticides, come from fossil fuels and palm oil, which cause high CO2 emissions, deforestation, and biodiversity loss. This is why we must find ways to sustainably produce these essential products.
We're biosurfers. Join us transforming waste into possibilities.
We propose to produce lignocene, a bio-based molecule that has both biosurfactant and biopesticide properties, produced by valorizing organic waste streams from other local industrial processes, endorsing circular economy while taking care of our planet without compromising our needs. Come along with us in this journey and we will tell you all about it.
So, what is lignocene, you might ask? Lignocene is a lipopeptide, a molecule that has a hydrophobic and a hydrophilic component, allowing to reduce surface tension between enemy phases like water and oil, helping stabilize emulsions for the production of personal care and household care products. But not only this, it also has antimicrobial properties, helping boost plants' natural immune system, being very useful for the production of biopesticides. Also, when comparing it to other biosurfactants like surfactant, it is a better chelating agent because it doesn't precipitate in hard water conditions and it is more efficient. This being represented by a lower CMC, which means that we require less amount of product to achieve the maximum mixture between these enemy phases. But as you know, a lot of bio-based processes have several challenges, and this is not the exception. Our main challenge is that its common way of production is through aerobic fermentation, and since it has a surfactant nature, it produces intense foaming, therefore requiring the use of antifoaming agents. But these affect the surfactant properties and make the downstream process expensive, hindering its economical scalability. But we have a solution for you. Our innovation is through anaerobic fermentation, where we don't produce foam and we don't require the use of antifoaming agents, making the purification process feasible. We achieve this through a facultative anaerobic strain of Bacillus echinniformis, and since oxygen is not toxic for it, we don't have to maintain strictly costly anaerobic conditions. Also, to address the low yield related to anaerobic conditions, we are using a genetically modified strain, which allows us to have a higher productivity of lignocene, and it also relates with the sporulation pathways of the strain, allowing to have lower sporulation, allowing it to be safer for industrial use. Also, in terms of extraction, we use green solvents like ethyl acetate, and to enhance our bioeconomy approach, we're valorizing side streams such as vinasse from the bioethanol production, which is a cheap side stream and is produced in significant quantities, therefore integrating circular economy into our process. This way, we produce lignocene, which is a multi-purpose ingredient. It is biodegradable and non-toxic, and our byproducts, which are rich in organic acids, can be further used for biogas production, which we can further utilize in our process.
But what is our process and technology? Here in our schematic is the simulation of 1 ton per year of lignocene. In the first stages from the upstream fermentation up to the first centrifugation, these are based on our experimentations. We further extended this to further separation and purification processes based on literature to demonstrate the scalability of our technology. Now our process begins with the media and inoculum preparation, followed by the anaerobic fermentation, whose broth is centrifuged to remove the biomass waste. The supernatant is then acidified to precipitate lignocene that will subsequently centrifuge to remove the waste supernatant. To achieve further purity, we employ solvent extraction and drying to achieve a purity of 93%. As you can see in our upstream and downstream processing, these are composed of simple unit processes that allows the higher potential of viability of scaling of our process. Moreover, most of our waste come from the centrifugation processes, have the potential to be treated and valorized, thus reducing both our costs and environmental impacts. Below are the material and energy balances that are the basis of our cost estimation. Now, how do we know that our process is economically viable? Based on the same simulation, we identified that the cost of research, building and starting up the plant is about $4.5 million, while the annual operating cost costs about $1.6 million. Since lignocene has not yet been commercialized, we identified the selling price of our product per kilogram by setting a payback goal of half the lifespan of our plant at 7.5 years. This is calculated as $2,200 per kilogram. To compare it to the market, since lignocene is about 10 times more effective as surfactant, to get the same results of 1,000 worth of surfactant, you would need $230 worth of lignocene. Further economic analysis shows a net present value of $2.2 million and an internal rate of return of 14.3% that is higher than our discount rate of 7%. While this is promising, we do know that our price is still on the high side, which is why we plan to do the following. On the first 2 years, we plan to optimize our process by doing further experimentations, considering our media and operating parameters to reduce our selling price by 40%. We also plan to integrate energy and solvent recovery in our process design to reduce our operating costs by 10 to 20%. Furthermore, we aim to situate ourselves in a biorefinery complex to partner with different companies and use their side streams as our substrates, thus reducing our operating costs by 7 to 10%. In the long run, we plan to implement more genetic engineering to increase the productivity of our strain by 2 to 5 times, thus reducing our price by the same margin to have a more competitive pricing and entry to new markets.
Now, to evaluate our environmental impact, we develop a life cycle analysis for the production of 1 gram of lignocene through anaerobic fermentation. Our system boundary is cradle to gate, meaning that we're not considering the end usage or disposal of lignocene since the main impact is in production. From all of these impacts, as you can see, the main impact is in climate change with 43.7 grams of CO2 equivalent. With this, we identified our main hotspots, which are the fermentation due to the use of steam for sterilization of our media and equipment, and our downstream process, specifically the liquid extraction due to the use of butanol. For this, we propose that our plant works within an industrial complex as part of the biorefinery unit so we can use steam waste streams from renewable sources to be able to maximize the energy efficiency. In terms of butanol, we plan on sourcing it from bio-based wheat straw instead of fossil-based sources, and we plan on recovering in the solvent extraction. Now, comparing it to other biosurfactants like surfactant, the best way to compare it is through the efficiency. So the functional unit in this case would be the grams of surfactant required to reach the optimal reduction of surface tension. As we mentioned, lignocene is more efficient, so it requires 10 times less product to achieve the same effect, generating over 700 times less emissions, having a lower environmental impact overall.
For the business aspect of our model, since lignocene is multi-purpose, our approach is to focus on 2 main niche markets first, phytosanitary and biopesticides. So this target approach will allow us to competitively price our product. And after we price our product, it will allow us to get enough revenue to further optimize the processes. And with enhancers efficiently processed, we can then have a more a competitive and adapted price. And therefore, we aim to later expand into other broad markets such as cosmetics, pharmaceuticals, and cleaning supplies. So these will all require surfactant as ingredients. And the first wave of our revenue stream will come from business to business contracts and, of course, product sales. So how do we actually know if other companies will be interested in collaborating? Since we're producing a bio-based ingredient, we are already aligning with their sustainable goal, and we do plan to work with companies that do want to achieve eco-friendly goals and produce these products. So we can look at Ecover and Evonik as good examples since they are already interested in developing bio-based chemicals. And another very important contributor to our success and revenue are our partnerships. So we have two main important partnerships. Firstly, the side stream providers. To be more specific, bioethanol producers who will provide us with vinasse. And in the future, we also plan to explore other side streams as well. And we cannot forget our own side stream, and hence the second partnership would be biogas producers, which will help us a lot in valorization of our generated fermentation waste. After providing the technical feasibility on lab scale, our scheme will not only be able to present a novel anaerobic approach to biosurfactant production, but it will also effectively valorize side stream effectively and at the same time enhancing the properties of biosurfactant or lignocin into another level. We also have a solid techno-economic assessment for marketing a product in many different applications, and this will allow an increase of profitability, versatility, and also it is very friendly to our beloved environment. So behind this idea is our amazing and multidisciplinary team. If you do believe in our idea and if you think that this innovation can make it to the market, please join us in transforming waste into possibilities. Merci beaucoup. Thank you.
Thank you.
Wow, thank you. Excellent and within the time. Merci beaucoup. I puzzled with one thing myself. That is, if you need 10 times less of the stuff, why don't you simply increase the price that you're going to sell it for?
Increases. The effectivity that we discussed is comparing with a similar biosurfactant, which is surfactant. But since, like, if you're gonna compare it to the general market of biosurfactants, we aim to lower our price to compete with those and to enter like markets as we mentioned earlier, such as the detergents or personal care, which has lower pricing in the use of these materials.
Okay, thanks. Sophia?
Thank you. I really enjoy your presentation. It's very good work. It was very clear. Are you expecting to have some issues or some problems in the follow-up of this project related to using genetically modified organisms?
Actually, since we don't, our final product won't have any genetically modified organism within, so we don't face any issues. And the system that we're going to use are not threatened by the usage of GMO because we're using only the genetic material that is within the cell. We just change the position of the gene within the genome, and so there is no external genetic material, so it should be okay.
To complement, since our product, which is lignocin, is extracellular, with our downstream processing, we plan to completely separate it from the GMO strain.
Yeah, but I can feel along the question that in organic, it might be possible that you could never use GMO in any production process, but you should check that out, I think. Lene.
I really enjoyed it, and I have to say that you are presenting very, very well. I'm impressed. I have a question in the sense of, are you sure you have freedom to operate, that other people have not kind of made a patent or something on lignocin, or even trademarks and so on, and using that? And this for the GMO, I just want to make sure that you understand. I mean, the other panel members are asking the question that there are several market segments which do not want GMO even though it's a secreted product. I know that from enzymes, secreted enzymes, many markets are not even for food or cosmetics and so on. So just the regulatory part, GMO and market, and this with the freedom to operate.
For the first question regarding other productions of licanicine, from our knowledge and with the group of our university we're working with, information regarding production of licanicine isn't a lot of it is not published and it's not very available. A lot of it is available for surfactant and it is well produced. Licanicine is very similar, just that it has advantages compared to surfactant. The problem is that its normal way of production is through aerobic fermentation. So until now, they haven't really developed any other process with anaerobic fermentation. This is like the innovative thing we've obtained through our results. Rafi, I think you could complement the GMO.
And for the GMO part, I think there are a lot of issues for labeling. So usually what people are afraid of when we do genetic engineering, we usually introduce some gene, and with it we have to introduce a gene that is coding for antibiotic resistance, for example, and that's a big issue. And in our example, there is not the case. So maybe it's just a matter of labeling, because we label everything as GMO, but in reality, in our case, it's just a small genetic enhancement of just putting some more promoters or changing the promoter from one to another from one gene to another. And also, we hope that the EU regulations will be more favorable to our part, and we think that it's going to that direction. So hopefully, we won't have any problems with the application.
All right. Simona.
Hi, in line with the other reviewers, thanks a lot for the presentation. It was really nice to follow. Probably it's a question that can also somehow solve this issue. Did you check if it is possible to use a solid phase peptide synthesis to produce this molecule? Could it be an option?
So far, we've done only fermentation, and we didn't use any solid media as like the food for our microbe to produce licanicine. But that could be an option. It is considered in the literature. There are some biosurfactants that are produced in that way, but we were still trying to produce it through fermentation.
Yeah, probably as a mitigation plan in the case, and also to take into account in terms of analyzing a bit the cost. It could be a nice work to be done behind. And on the other side, revising the report, I think that, the market analysis was perfect, but I was thinking, are you also calculating how much it will cost to put in place the production process?
They showed an
The
investment
production
figure, didn't
process
they?
of
Yeah.
yes, the cost of building the plant and the annual operating cost of producing the product itself was calculated, and we showed the slide. So the operating cost annually to produce 1 ton of licanicin per year is about $1.6 million. At that.
Okay.
Okay. Kevin?
Sure, yeah, two things. One, I'm going to go back to the GMO. As somebody who's developed a technology using GMO and gone through the regulatory process, there is a way through. It's a painful, long way through, but you have to demonstrate actually that there's no DNA present in your product because it's extracellular. I take Lena's point about enzymes, but if you actually we had to do multiple PCR reactions, different tests to demonstrate that there is actually no DNA in the product, either of an antibiotic resistance or something from the plasmid or something from the chromosome. There's a lot of tests, but there is a way through. So I think you can, it's just painful, but you can get through. The other point I'd make is ethyl acetate. You addressed butanol, and you said you use bio-based wheat, and maybe I missed it. What's your source of ethyl acetate?
Our source of ethyl acetate is produced from renewable resources, although ethyl acetate compared to other solvents is considered a green solvent. Not compared to butanol in terms of our LCA, the program that we're using is only considering in the database fossil-based sources. So that's why when we do the LCA, the analysis of the butanol comes up as one major
red flag
affectant. Yeah. So, but in terms of like databases, a lot of databases are not still available that are coming from renewable resources. So we weren't able to put that one, but we plan on using and sourcing it from renewable resources to have a lower impact.
Very good. And can I just follow up then, because you mentioned that, which is a very good idea, the recovery of the butanol, and I assume recovery of the ethyl acetate in your process, which is really good because that's circular, but there is an energy cost to that. And have you included that energy cost in your life cycle analysis for the solvent recovery?
We have not included that yet in our
Yeah.
LCA. We have,
Okay.
that's why we proposed on including it in further experiments, because we haven't calculated those energy costs yet.
Yes. So to add to his answer, because this is more, it's both the environmental impacts and the economic impacts are quite related. We haven't employed in our simulation, we haven't employed the solvent recovery, but we're like looking into that side that it might be possible to reduce costs. So it will go hand in hand that if we ever try to simulate or look into that aspect, it will also go to the life cycle analysis.
Very good. I think it will impact your cost. But when you're doing those tests, and I should have said that to previous speakers as well, on the cost, look at the scale of operation, because that can significantly impact your cost. Because I think when you're starting out, you might think, oh, how much does 1 kilo or 1 unit cost? Yeah, but you must think in the terms of millions. Yeah, and that will have a dramatic impact on your LCA. But very nice, yeah, really nice work. Thanks very much.
One more comment, if I may.
Yeah, sure.
I also forgot to mention, before we started our experiments with the GMO strain, we had to prove it that it's safe to use it in the lab. So we kind of have all the certificate that it's actually safe to use. So there is no hazard coming from the strain.
Great, thanks very much.
Okay, that was the time. I'm sorry, Elena, for you. Thank you very much.
Thank you very
merci
Thank you very much.
Obrigado.
Thank you.
And last but
Merci.
not least, Cap con Cap. We don't see many Thai here. So thank you very much. We
Thank
move
you.
to the next team.
Thank you.
Germany.
Yes.
Hello, can
Hello.
you hear
Bitte,
us?
Deutschland. Seid ihr alle da?
Yes, we're here. Let me share my screen real quick. All right. Can you see the presentation?
Yeah, go ahead.
Thank you.
So, hello everyone. We are the team BrewRenew, and we are from Germany. And yeah, we are the German part for the BISC-E challenge. And obviously, we make something with beer. And I'm happy to present you our idea. So, with our idea, we face two problems. Firstly, the biological process engineering is mostly based on fossil resources, and in order to gain some high value products. And secondly, the industry has residual streams which are not used valuable right now. So what we do is we combine both of the problems and get rid of the issues, and we keep the benefits. So what we do is we have brewer spent grain, which is a residue stream from the brewing industry, give it into our process, and we get the high value products. And all of it in our startup philosophy from grain to gain, brewing the bio-based value chain. Okay, so now let's give it some substance. As the feedstock, as I told you, the brewer spent grain has a market size of 38 million tons per year globally, with a market price of 35 euros per ton. So this is a very low price product from the brewing industry, which shows us indirectly that it's not of a very industrial interest right now. Our product, the ergosterols, which are produced from the fungi we use, has a market size of 150 tons per year globally. And yeah, this shows us that a market for the ergosterols already exists. Okay, but are we big enough with our idea to play a role in the market? So let's start with the mycelium. It's a product from the fungi. And the mycelium has a market size of 2.79 billion US dollars. From the mycelium, you can extract the sterols with a market size of 1 billion US dollars. And the potential market with 50 million US dollars is what we want to reach. So considering the globally produced Brewers bench grain, we can potentially reach this market share. Okay, and now Sabrina will continue.
Yeah. So Bendix has more or less given us the green light to use the global problem as our market. And to prove that we're not talking about a big dream from our side, let me quickly take you through our biorefinery principle, which we've developed and already tested in our lab as a proof of principle. So while you enjoy your delicious beer, the BISC-E, so brewer's spent grain, is produced and passed to us by our brewery partners. Then we do mechanical thermal pretreatment, and we receive a liquid and a solid fraction, which we process to our cascade in our biorefinery. So we take the liquid as a sugar and nutrition-rich cultivation media for algae, and we do it in, well, let's break it down to a fed batch system. On the other side, we use the lignocellulosic fraction as substrate for fungal cultivation. But the innovative clue that brought us to where we are now is that we combine the lignocellulosic solid with the algae harvest. So we receive a fungi, which is new in the world of fungi plus algae by combining it. So in the end, we downstream the mycelium of the pillar fungus to the sterols, which Bendix is showing you right now. And the algae we can use to produce or to downstream it to valuable high-value products, such as fucosyanin, which is a pigment. We already used it to produce some gummy bears. Well, other than that, some PUFAs or antiviral substances, which we can use in our Bavarian region to work on fish sicknesses. So we receive the products, but the great stride is that, or the innovative breakthrough is that we symbiotically link algae and fungi cultivation. But however, this is not where we stop the idea of circular economy, because we can also use the kettle wash water plus excess CO2 plus waste heat lower than 60 degrees, which is normally not usable in industry fields, within our biorefinery. So, well, actually you can see that we are not selling an, well, specific product as the other ones, as the other teams before us did. So we have a lot of process engineering investment, but we as a young startup want to approach it in view to continuous growth. So after finding financial support and we are up and running, we want to get straight down to work with our own laboratory. We'll team up with further brewery partners, but also product buyers, and get our units up and working. And then we target to scale up our process individually to our partners. So once we are more established, we'll optimize our process and look for new products from the algae, for example, but also for feedstock. So we could go for wine production, for example, or Kellogg's cereals, waste streams. But to grow sustainably, we have to keep an eye on our market we operate in, so our competition. And our competitors on one side, regarding feedstock, they use the BISC-E for animal feeds and in the energy generating market. But both of those value chains are pretty low profit. And we have to say that BISC-E is linked to a couple of problems in this field or in its use there. And on top of that, we are right now working on a proof of principle to show that our bioprocess can be integrated into these established streams. So we are not producing any conflicts of interest. And we already received a lot of feedback from biogas producers or farmers that they are interested in talking to us and finding new solutions because they have a lot of agricultural problems to face. And then we have some new competitors on the market which do use the material, but what's unique to us is that we can handle or upcycle the big pile of BISC and not only small amounts, and we're talking about tons per day worldwide. Then compared to our competitors on product side, so our sterols or egosterols, well, they are based on petroleum, on agriculture or animal agriculture and crop plants. So these aren't beneficial due to ethical concerns, inefficient land use, and well, the depletion of fossil resources. So they are not ecological and therefore not really future-proof in our view. And I hope that the future will go this part of bioeconomical thinking. So our idea has already proven itself, but we are just in the beginning of establishing it. So with further developments, we can climb the competition ladder concerning economical, but also ecological regards. And that's, well, because we have even more key advantages on our side. So once our process is a phase 3 biorefinery, sorry, which means that we are completely part of circular economy. Then on top of that, we combine this with upcycling by feeding energy light into our units. And thus we generate biomolecules or new biomolecules by algae growth. Then we combine it to biotransform the lignocellulose in the time-efficient process.
10 minutes already.
Okay, thank you. Fungal cultivation into our high-value products. And other researchers haven't been able to break down the lignocellulose raw material, but with our symbiotic idea, it works. So finally, in the end, we have a modular process design which allows dynamical adaptivity, and we can flexibly scale our process to markets, to breweries, but also regarding new feedstocks and products. And so all in all, you can say that we have a concept and a proven concept of a techno-economical or ecological or eco-friendly working biorefinery, which is ready to generate value, and therefore we integrate bioeconomy within a sustainable development.
Okay, and this is our team. Sabrina is the one who drives the idea forward and the team forward. Natalie and me, we are powering the innovation and engineering part with our expertise in this field. Torsten, he is the new and fresh one, and he is thinking out of the box because of his freshness. And Lucas and Kai, they are fueling the financial growth of our team. Yes. Then
let's say thank you for your attention.
And
post.
Okay, thank you.
Okay, and now it's time to act.
I see a question from Lena, I think.
Okay.
Thank you so much. A fantastic presentation. And I have to say, I have seen many products made from brewer spent grain in my time. But this is the first time I see the focus on the ergosterol as a vitamin D. But I have a question. The mycelium you are using only actually a very small part of the fungal biomass. Have you considered to make another high-value product from the fungal biomass, for instance, beta-glucans or something else?
So in the beginning, we want to focus on the sterols because there's a wide range to the very high variety of products we can use from the fungi and from the algae itself. But yeah, in the beginning, it's good for us to focus it and narrow it down, and then we can think about further products in a later step.
Yeah, but in our proof of principle in the lab, we actually used a different kind of or different species of fungi, which produces a red pigment. So we can also say that this would work. We just saw a bigger market for sterols. But so our supervisor from the lab, he also said that once we prove that this or those fungi work, we can compare it to others. So there's a wide open field, but as we have just a complex process and a big palette or cascade of products, we wanted to narrow it down and find our special product.
Erwin?
Yeah, thanks very much. Really interesting. As Lynn has said, it's a really novel approach to produce the ergosterol. Can I ask you about your 150 tons of ergosterol? That's a total global market, yeah?
Yes. Yeah.
Yeah. So I want to ask you about the yield. What is the yield of your ergosterol from your brewer spent grain? And the reason I'm asking you that is to understand what percentage of the total tonnage of brewer spent grain are you going to use?
Okay, so about the yield, we did not test this one or the productivity of the fungi. It's not tested yet because we did our experiments with the C. morei, another fungi. But yeah, so
maybe you think about it, and what I can say is that our proof of principle was, first of all, can we grow the fungi? And then the yield we receive more or less from literature, in which they used actually brewer spent grain to produce fungi or cultivate fungi, but in a less efficient way. So we used their yield per biomass or per kilogram biomass fungi or mycelium, and we didn't downstream the fungi to the product because right now to be honest, we just don't have the equipment and the money to get all the downstreaming units. So we have to rely on literature.
Sure, that's fine, because it's a proof of concept, so that's fine. But what I'm trying to get at, I suppose, is how much of all the brewer spent grain, even in Germany, for example, regardless of the world, what percentage of that will you use? I'm trying to understand the business feasibility around using that spent grain. Are you going to ask them for everything? Or are you going to ask them for 5% of the total grain available?
So actually that question is clever because every brewery has just traditional structures of selling their brewer spent grain right now. So talking to our partners results in individual solutions. So we right now have a specific partner in our city, which is very interested in handing over all of their brewer spent grain, for example, because it also broadens their palette of products. Because they have to face problems in agriculture, in biogas plants, and so on. And actually, we can pass on our remaining biomass to those customers again. So talking to those partners we already have, they are open up to giving us all of it, but maybe not next year, but developing it. So it's just a big market of breweries. There are some that produce, 100 liters per month. Others produce tons per weak, and that results in our unit size or in our scale
You
up.
just keep talking because you don't want to answer Kevin. The main reason he's in the jury is indeed he's a very clever man asking very clever questions. We move to Manfred. Thank you.
Thanks very much.
Sorry. Thank you for the presentation and all the explanations. You said you aim on a market share of $50 million. How did you calculate that?
So yeah, from the global, yeah, the in total global amount of brewer spent grain which is produced, we took yeah 10% roundabout, and from those 10% we can reach this market share. As there's assumption of the sterol price right now from our side, and then we calculated it with how much sterol we can produce from or could produce from the fungi, and then this is our market share.
Okay, Sophia.
Thank you. Very good idea, but I would like to know, what do you need to move forward beyond money, investment, and equipment to go beyond that proof of concept? What do you need? What are the following steps?
Partners would be nice. So we need some further partners in the biogas, from the biogas side, then we can do the proof of concept there and integrate our system there. Then product partners that we can enter the market easily with contracts, for example, that we can give our product to them. And
so you believe you reach the level of research that you need to move to those steps?
Yes, we believe that we can do it.
Actually, to give you the background of our team, we started the idea with algae and tried to use the liquid phase as a cultivation media. And it did work, but then, well, it was more or less an inconvenient, or, well, luckily that it happened, that we started using fungi in our lab, and then we just tried it out of fun. And then we were surprised how good it works. So our background is more or less algae cultivation, and we are more focused on the market of algae products. But now it just opened our eyes that we can combine it with fungi. So what would help us is just get us insights to partners in the mycelium world, because we are quite new to it, but we are motivated to learn. So for the pigments, we have partners. For the antiviral substance, we have partners. For the chlorella,
I'm slowly
we have
having
partners.
to stop you now.
Yeah.
Because we passed the time. Thank you. Dankeschön. Und auf Wiedersehen.
Thank you.
At the end of the day. See you. Could you stop sharing, please? Because we are basically right. That's it. Okay, we move to Pavlina Pesheva Mustakova from Bulgaria. Bulgaria, are you there? Waiting for Bulgaria? Oopsie.
Technical problems? Are they in the room? Does Nelo know if they're actually in the meeting?
I can check. Yeah, Janev is playing some music here. I blocked him. Pavlina, let me see. Don't find her. No, Pavlina. Okay, we have two options. We skip them, or we ask Latvia if they are there to start. And that means that Calve should be here. And he isn't here. So then we just wait. Too bad.
It's okay. Maybe Nelo, can you contact them and see if they're having problems accessing the meeting?
The silent secret, Kevin, is that Nelo is no longer in the meeting.
Okay. Okay.
He has to drive for 2 hours, and he said, you will be okay. So you see him in the list. He has left his small device there.
Okay.
In his office, but he's not physically attending.
Okay.
Well, they could have been mixing up the hour. There's 1 hour time difference, I see.
But that means they would be earlier, no? They would be an hour
Suppose.
earlier. Yeah.
Yeah, I suppose.
It's only the Portuguese and the Irish that are way behind. We're an hour behind. Yeah.
I don't find any of them names on the list, actually. Angelina, no. No, none of the Bulgarian team is here.
So maybe then we can wait the 20 minutes and then because the Latvians may not turn up until 5 minutes before their time. Yeah.
I suppose so. So yeah, well, I'm sorry for them. Let's be back at 11:50 sharp, then, just before 11:50.
That's 25 minutes from now. Is
Okay.
that correct?
Yeah, because we include a break of 10 minutes.
Okay.
So we waited 5 minutes, and that's about it. So
10 to
sorry.
12?
Yeah, 10 to 12 sharp.
Perfect.
Okay.
All right. Thank you.
I realized I have the sunglasses on.
No, you don't.
No, but I moved away for a second because I had my sunglasses on and it looked
Okay.
weird.
All right. Alvis, I saw him. Latvia.
Yes.
Yeah.
Can you hear me?
Yes, we can hear you. You could start presenting.
Okay, is it visible? Is it everything? Okay.
You're fine. Go ahead.
Go ahead.
So good afternoon. Can you hear me?
Yeah.
Okay. So we are Team Latvia and we represent Riga Technical University and Latvian State Institute of Wood Chemistry. The goal of these two institutions is to make new and science-based methods and materials for green transition from bio-waste or wood. And today we will try to introduce you to idea of using industrial waste into and turning them into battery-grade carbon materials for green transition. So why chicken feathers? It is estimated that carbon might double in the next 5 years. And for now, unfortunately, most of this carbon is derived from fossil fuels, for example, different soot. And in our experiments in laboratory, we have shown that if we used activated charcoal, which can be produced from different biomasses, we can increase specific capacity of electrodes and improve the electrochemical properties so we can produce less carbon material and derived it from natural sources. And for now, we chose chicken feathers because for now they are industrial waste. There are no other uses, and in this case, for this factory, they are just deposited into landfill. And our estimates show that we can produce same quality material with the same price as industrially available materials.
So there is the need for highly effective carbon materials in the electrochemical industry, and for now they could be produced through 3 steps: carbonization, activation, and nitrogen doping, which requires high temperatures and use of chemicals like DCDA and DMF. So we propose to use biomass already rich in nitrogen, such as chicken feathers, for the carbonization, so we can avoid the nitrogen doping step, which is expensive and chemically demanding, because the nitrogen would be in the material from the start. And this would be also a great way to recycle and reuse the waste materials such as chicken feathers. So in our case, the source of nitrogen for these carbon materials would be chicken feathers, as they contain mostly proteins that are rich in nitrogen. The second waste material we can integrate in this biorefinery cycle would be used wheat straw from the chicken bedding material. This contains a lot of cellulose and lignin, which are great for forming the carbon itself, and it increases the yield, and it will increase the effectiveness of nitrogen retention, which means that less nitrogen from the chicken feathers would be lost to gases, for example. So combining these two and carbonizing would give us biochar, nitrogen-rich biochar, which has a stable carbon structure from the cellulose and lignin, and also has the nitrogen-containing functional groups, which improve the electrochemical properties of carbon materials by increasing the wetting properties and charge transfer and other properties. First step would be pre-treatment of these materials. The chicken feathers are obtained from the chickens using hot steam, so they are very wet, maybe even over 50% moisture content. So they definitely need to be dried first. Then both wheat straw and chicken feathers would be crushed to ensure a finer particle size and more homogeneous mixing between the two materials. The second step would be carbonization to obtain the nitrogen-rich biochar. And this would produce also bio-oil and flue gas. The flue gas can be easily repurposed by burning it to provide some of the energy required for the same carbonization process. And bio-oil could be an interesting new material to study further. It could contain a lot of different chemicals, so it also has some potential. The nitrogen-rich biochar would have a problem that it doesn't have a high surface area, so activation would also be necessary to increase this surface area. Physical activation would most likely be the best option, as it's more used in large-scale continuous processes. After the activation step, we'd also need to wash this biochar to get rid of any impurities and ash that would be blocking the newly formed pores. And this is performed through washing with the HCl solution and water. This would probably produce the only big pollutant from our process, which would be like this HCl brine and salt solution. We need to think about how to minimize this step. And so after drying and quality control, we would have our nitrogen-doped activated biochar ready for electrochemical applications. Also, the thermal energy left from the physical activation could be repurposed for the drying processes required in this technological scheme. Here you can see the mass balance of this process. We can see that the yield, the activated biochar yield, is only 40%, which seems like not much. But if we take into account that we're recycling low value waste materials, and secondly, the low yield is because both of the processes, carbonization, physical activation, are destructive by nature. Their effect is achieved because the materials is somewhat destroyed. So this is the reason why only 14% yield. Here is an approximate scheme of the pyrolysis of the carbonization phase. We intend to use a fixed bed batch reactor because the feathers melt, and so it's hard to use them in a continuous process. The carbonization would receive energy from burning fuel and air, and when the process starts, we will also burn the pyrolysis gases, the flue gas, with the fuel and air to reduce costs. And after condensing the bio oil from the secondary flue gas and purifying it, we could release it to atmosphere. It will contain probably nitrogen, carbon dioxide, maybe, and we would have our biochar. This is the scheme for the activation process. Here we can use a continuous process because the biochar powder or granules are very easy to work with.
You have been talking for 10 minutes.
Oh, okay. So I'll move on to the next part.
Okay, so at this point, you might be asking yourself whether this chicken feather biochar thing is environmentally friendly. The short answer is yes, but realistically, it is a bit more complicated than that, since our technology does include a few environmentally unsound steps. Our technological process is energy intensive, and it also does include washing the material with copious amounts of hydrochloric acid. However, the high temperature required for pyrolysis also allows us to off the germs that can be present on chicken feathers, and it also decreases the probability of the spread of serious diseases like the avian flu. Subjecting bird waste to high temperatures can also get rid of organic pharmaceuticals that can impact the antimicrobial resistance of pathogens all around us. And not only that, but by burning chicken feathers and litter, we can drastically decrease the amount of nitrate pollution, making chicken rearing a safer industry and allowing you to have some fun in the water without actually worrying about catching a nasty bug. Please. Thanks. But the good things don't really end there. Because of the continuous developments in recycling technologies, the material could be regenerated. Then it could potentially be used in batteries, fuel cells, and the sort, providing energy to the poultry farming and to us, of course. And even if the regenerated material is unfit for electrochemical purposes, it could still be used as a pigment, as a filler, or as an additive. And since biochar is inert and stable, it can also be used in carbon sequestration. While our biochar will most certainly not change the world, it might aid in making some things a bit safer and a bit better. So if we can try to improve the things around us even a tiny little bit, then really, why not? Thank you all for listening to our pitch, even if it was a bit long, and best of luck to everyone else.
Okay, thank you. Could you stop sharing, please? The first one to push the button was Manfred. You're mute, Manfred, after all those years. Come on.
Thank you for this presentation, especially for presenting the technical process. I learned from your written documents that this biochar finds its application in electrochemistry. Could you please give us an example of the role and the value of biochar in these processes?
We have experimented different biomasses in our laboratory, and for example, in our case, we use it as a conductive material for we work with decoupled electrolysis, and we use this carbon material as conductive additive. And for now, available commercially available additives are fossil fuel based. And in this case, we studied these naturally occurring by different carbon materials, and they showed much better specific capacity values, and they were, in our case, much more presentable in the electrochemical electrolysis processes. Battery grade carbon is still in the works.
Okay, Lena.
I really enjoyed it, and I want to express appreciation that you have seen that the stored feather, which are almost mountains globally, is a risk of especially fungal infections on human mycosis, dermatophytes. But it's also I want then to ask the question: are you aware of that kind of a fungal inoculum of pathogens can also be a worker's health risk when you are receiving the biomass you are going to use for the product? And in that sense, I would also like to ask the other part, pyrolysis can also lead to toxic compounds itself, which are not necessarily elucidated for that specific feedstock. So those two, safety, workers' health and safety.
Yes, thank you for the question. I think in terms of safety, it would be about the same as transporting it somewhere or using it as animal feed. It would probably involve all the same risks. And about the pyrolysis pathogens, chemicals, the step where we burn the pyrolysis gases, I think that would destroy some of the more dangerous compounds, and effective treatment of the bio oil and the leftover gases would probably minimize all these risks.
Thank you for your answer. I want you to make sure that you also are aware of that the feather, as you said, for animal feed, it is not digestible by animals. So that kind of application is not your real competitor for the feedstock. But it can be enzymatically, and you should be aware of that, because now there is an enzyme treatment where you can make that into protein-rich animal feed. So in that sense, for future competition for the feedstock, just for you to be aware.
Okay, thanks, Lena. Sophia, please.
Thank you. Congratulations on your work. I would like to ask you a small question related to the efficiency of the procedure. Have you done any prior research related to the efficiency of the procedure? Because you have two, if I understood correctly, 2 kilograms of raw material, one of feathers and the other one of the straw, that will regenerate 140 grams of biochar, but will disposal around 20 liters of HCl brine, right? So it seems to me that we have to improve this efficiency. Do you agree? Can you comment on this?
The efficiency of the produced acrylic biochar, the 14%, I don't really know if that can be improved. To clarify, it's from 1 kilogram of biomass, that was 140 grams, not from 2 kilograms. But
Sorry, I was not questioning the 14% of biochar, but instead the disposal of 20 liters per kilogram of raw material of HCl brine.
Okay, yes.
So I understand that biochar, it's only 14%. I understand that correctly. It doesn't seem a very different number from what I'm used to it. But once we are talking about circular economy, and we have 20 liters per kilogram of feathers that will be disposal, it's HCl. Can we have here some work to do, or that can be done to improve this efficiency?
Yes, definitely. Maybe we can lower the amount produced, or maybe we can find application in the chicken industry, for example, disinfection or cleaning something.
Okay, 1 minute left. Kevin, please.
Sure, yeah. Thanks very much again for a very interesting presentation. I know a little bit about pyrolysis, but not too much. But the question I have is, you said that you need a fixed bed batch reactor is required because the feathers melt, so they get sticky. Is there a way in mixing in other substrates to help maybe with the processability of the feathers?
Yes, the straw would be the idea, but we don't really know how effective it would be to prevent the sticking and the melting. But the straw is the idea that we would somewhat help also the sticking and melting.
Okay, great. So it is a possibility that you could mix substrates. Yeah. Okay, great. Thanks very much. Thank you. Very interesting.
It's biochar. Yes, you should be able to. 9 seconds left, so no other questions. Manfred, you withdraw it, right? Yep. Okay, let's stop here. Thank you very much.
Thank you.
And we move on to waste no carotenoids from Croatia. Are you guys ready?
Yeah.
Please share your screen.
Just a second.
Okay, Nicola.
Can you see?
It's coming, I suppose. Yep, you're on.
Okay,
Go ahead.
just wait a second. I'm having some problems. Just a second.
We see the moon now.
Oh, yeah. Let me try again. Something went wrong with that projection. So, okay, here we are.
Okay.
So, hello everyone. My name is Nikola, and I'm team captain of Croatia's team Waste No Carotenoids. Here today with me are my colleagues Barbara and Carla, and our mentor, Professor Christina. So, I'd like to start with a product most of you are familiar with, and those are eggs. Wait. But more specifically, I would like to talk about egg yolk. So why does it matter and why should you care? Egg yolk color is important for consumers when they are choosing to buy eggs again from the same producer. In fact, so important that there's a scale created just for grading egg yolk color. So let me paint you a picture here. You go to a store and you buy yourself some eggs. You come home, you want to make an omelet. You crack open an egg and you see egg yolk is just too pale. What goes to your mind? Maybe the chicken has been raised in such horrible conditions. Maybe something is wrong with the egg. And on the other side, if it's too bright, too intense, you would also think there's something unnatural happening here. What are they putting in their feed and so on? And I guess most consumers would not buy from the same producer again. But there's actually a grade of color, egg yolk color, which is different in every market, which is most desirable for consumers. So producers are trying to achieve that color by putting synthetic carotenoids into feed of laying chickens, and that is causing some concern for customers because they are getting more and more informed and they care more about what they buy and what they consume. But also, those synthetic carotenoids are just used for color enhancement, but they don't increase carotenoid content in egg yolk, which in my opinion is a big wasted opportunity because egg yolk is source of liposoluble bioactive compounds, and to which I will circle back in a second. But now I want to talk about the carotenoids. So what are even they? Well, they are a group of compounds that are bioactive, and they are usually pigments in various plants. And here we listed some of them: beta-carotene, beta-cryptoxanthin, zeaxanthin, and lutein. And some of them are precursors of vitamin A in human and animal body. They are also good for skin and good for immune system. They are also used in body as antioxidants, and they are in general good for human health. So what's the idea here? Our idea is to encapsulate natural carotenoids designed for egg yolk pigmentation so we can get that perfect egg yolk color. And also, while chicken consuming those the capsules would be used for feeding chicken. And while consuming those capsules, they would store these carotenoids in egg yolk, and they will be later available for human consumption. So how do we do it and why should we do it? But because we want to get away from synthetic carotenoids and we want to use biowaste as alternative. By encapsulation, we get stable and slow releasing carotenoids, because if you just put a powder in their feed, they would be over-concentrated and most of them would not be digested and they would just go to waste. Also, we base our production to be eco-friendly and we want to deliver healthy and natural diet for laying hens and for humans. So I said bio-waste. Why should we use bio-waste as a source of carotenoids? Here are some examples of grassland bio-waste, peach pulp, tomato waste, and pumpkin flesh waste. As you can see, they're all good sources of lutein, beta-carotene, zeaxanthin, and lycopene. And there's also abundance of bio-waste around. So what's our final product? We want to create capsules that consist of 25% of beta-carotene and beta-cryptoxanthin, which are red pigmented carotenoids, and also 75% of zeaxanthin and lutein, which are yellow pigmented carotenoids. We think that's ideal carotenoid profile for egg yolk color and also for carotenoid profile in egg yolk. And we encapsulate them, as I said, because of the slow release. So what do we need for production? Firstly, we need the truck fleet because we want to make strategic partnerships with cities and with vegetable processing factories so we can deliver all of that bio-waste to our production facility. We also need a control laboratory, production facility, and because we're dealing with great volume of bio-waste, we want to use manipulation machinery. So let me walk you through the 9 steps of production. Firstly, the trucks will come to our control laboratory where bio-waste will be sampled. So we can search for heavy metals, pesticide residues, and also mycotoxins because we are afraid that they might get extracted as well with carotenoids to the capsules. So we want to avoid that because they could pose a serious health risk for humans and for animals. If everything is all right with raw materials, then comes the vacuum drying. Why vacuum drying? Because with it we can remove water on lower temperatures, and that's very important because carotenoids are thermolabile, which means under higher temperatures their structure collapses. So after drying, there comes grinding because we want to ensure a larger reaction surface so we get better yields. And after material has been grinded, it goes to extractor, which is equipped with ultrasonic probe, so we can collapse the cell wall and carotenoids can move out freely and then can be easily extracted. After around hour and a half of extraction comes evaporation. We are removing ethanol, and we can also get 90% of used ethanol back, so we can use it in the next extraction. Then when we have only carotenoid residue, we have to analyze it so we are sure that it's up to 25 red pigmented and 75 yellow pigmented carotenoids. And if it's still all right, we can encapsulate it. And again, we sample it so that we are sure that capsules consist of desired carotenoid content so that what is declared we can sell. And then if again, everything is all right. Those capsules can be packed in UV protecting packaging because, again, carotenoids are unstable under UV light. And we also want to put their instructions for usage because even if we have the best product, if the farmers don't know how to use it, they will not get that ideal profile and that ideal color. So it's all a great story, but is it economically feasible? Well, we believe so. Here's our income statement, and with proposed facility of production, we believe we can produce around 3,700 kilograms of capsules annually. And because we recycle ethanol, which is the biggest expense in our production, it lowers our price, our production costs significantly. So they're around 475, and they can be sold per kilogram much higher. So that gives us ability to lower our prices if a situation on market is turbulent or if we struggle to sell our product. Also, with greater profits, there's a quick return of investment. But it's not all about money. And I would like to step back here a bit and show you this current management of bio-waste. So it's usually used for converting to fertilizer or plant fertilization, or it can be used for producing biogas or animal feed. But while looking at this, we thought, is that really all we can do? Because with dealing with larger problems as global warming and sustainability, we believe it's not just enough to come up with a solution, but to build upon it and get as much from it as we can. So with this introduction of this step in management of bio-waste, we are making circular economy more effective because we are using literal bio-waste and turning it into highly available product. Also, we want to create a sustainable and eco-friendly production. With encapsulation, we increase stability of carotenoids and ensure a longer shelf life. And also, there's no need for over-concentration. And we also produce a bio-derived product. So, for conclusion, I would like to say we want to create ecologically acceptable and higher quality eggs by giving farmers opportunity to buy ecologically acquired carotenoids, which will in return give health benefits for both animal and humans. And while doing that, we want to upgrade food waste management and acquire highly available products. Thank you for your attention.
Well, thanks. That's well beyond time.
Oh.
So, the moon again. Please stop sharing so we can start the question around. Yeah, Manfred is there.
Thank you for presenting a strategy to really yellow eggs. Your raw material is a seasonal product and might vary in composition and is complex and is normally difficult to handle. On the other hand, you need a raw material for your process which matches a specification. So how do you manage that? Is your process so robust that it can deal with all the variations you can expect, or how do you do that?
Yeah, so basically that's why we are sampling carotenoid profile after extraction, so we can see which content of carotenoids we have there. So we can adjust it with, the grassland biowaste has more of lutein and less of beta-carotene and beta-cryptoxanthin, but pumpkins have more of them. So when we're extracting carotenoids from pumpkins, we can store that in a refrigerated area, and we can again mix it with grassland biowaste-based extract, so we can get that ideal carotenoid profile.
Okay, thanks, Lena.
Excellent ideas, very innovative, and presentation is really good. I wonder, I would like to challenge you for your concept. How will you compete with a feed additive which don't need slow release because it is dosed according to how much is needed for giving good egg color? That is and you could make it from a special. I mean, it could be from peels of carrots and pumpkins, etc.
Okay. Well, we believe that with slow releasing, they're more adjustable, and we can use more of the carotenoids. But if you just feed them, with carrot peels and pumpkin peels, they're also not that bioavailable because they're less available from plants and more available from those capsules.
But there's also a problem of dietary fiber because we cannot get chicken to eat too much fiber because it won't get digested. Yeah. They have a very small window of dietary fiber they could eat in a day, let's say.
I really liked your answer. I have to say, sorry, Kees, but that was very good answer, and you thought about it. The other, just consider if you would still like to call your residue a waste, because it's difficult to get into the food chain and feed chain. If you call it a waste, to me, it sounds like it's a residue and not something dirty or toxic.
Waste has a separate legislative system in the entire EU, so I never use that word. Side stream, second mainstream, whatever you want, but never waste.
Okay.
Semantics, yes. But very important.
Okay.
Kevin, go ahead.
Yeah, thanks very much, Kees. I'm going to ask you about material use. So you have packaging to protect the product from UV light, and you also have encapsulation. And maybe I missed it, I apologize, I was scrambling down to get notes on percentages of beta-carotene, etc. But what materials are you going to use for encapsulation and for packaging?
Okay.
Okay,
encapsulation. Thank you. So for encapsulation, we would use starch matrix because it is highly digestible in the digestive tract of laying hens. And for the packaging, we would use natron bags, which have material that is sure to protect carotenoids from any kind of UV lights.
Okay, and is the packaging, so this obviously the encapsulation is bio-based with starch, and then the packaging, is that bio-based or is it fossil-based?
It's bio-based.
Okay. Great, thanks very much. Very interesting presentation. Great. Thanks.
Thank you.
Thank you.
Simona.
I have a question maybe regarding the process, the ultrasound assisted extraction. So which is the scalability, and also are you also planning to have an in-continuous process?
So with all, so is it scalable? Yeah, we believe so, because so we would put the probe inside the extractor, and there are also some variations of the system. We can put a probe inside the extractor and then try to steer ethanol around it, but we can also have extractor the raw material can float freely inside the extractor, and there will be a pipe around it. So the ethanol with the raw material, which is grinded, goes through a pipe where inside is a ultrasonic probe, which then collapses cell wall, and the ethanol with the raw material circulates all the time. So everything is, yeah.
We should maybe enhance the seasonality, because, for example, in summer we have a lot of tomatoes. For example, passata production, you have the pulp and the skin of tomatoes. We could use, for example, that in the summer, and in the what's the word? In autumn, yeah, sorry. In autumn, we could use pumpkins, because we all know they are very good source of carotenoids. So we can say that the production is seasonal, but in each season, we have very good sources of carotenoids.
Okay, thanks. Just have you already tested the process in continuous? Because my experience is that it's not that easy to be optimized, and especially if you have seasonal raw material, not just the process, but also all the process parameter must be optimized depending on the raw material and so on.
So we did something similar. We produced some capsules and fed them to laying hens. But also, you said, is it seasonal? There's also, I think the vegetable plants are doing the whole year, and they're importing also vegetables from outside and processing them. So again, through winter and through winter, we also have some materials from where we can extract those carotenoids. And also, if we plan in the future, if we know in winter there may be less of beta carotene, less of waste with beta carotene, we can store those extracts with beta carotene for winter, so then we can mix it again with other extracts.
Okay, Sophia.
Yeah. Thank you. I really enjoy your presentation. Kevin already did one of my questions, but I have another one. Have you tested the time frame of your product from the time it's produced until it can be consumed? Do you know the average expiration period?
Yeah, well, we actually tested the stability of carotenoids under several conditions: lower temperatures, higher temperatures, under UV light, and without it. So for now, we have made a test for up to 1 month. So under
already in the capsules.
Yeah.
Okay. I'm not sure if I can do another point. Aren't you afraid that your package can jeopardize your business model in the future?
In which way?
And that it can be higher costs than your product itself.
So do you think there may be higher cost of production?
No, of your package.
Oh, okay,
Package
yeah,
process.
but still, production costs are much lower than other natural derived carotenoids. So I think I would say a lot cheaper is production. So I would say, even if the price of packaging goes up, I think there's still a margin that can go up and we'll still be all right.
All right, thank you. Manfred, quickly, please.
Well, your product, your idea can be a perfect example of circular economy. If you recycle all the materials you handle and you produce a lot of wastewater and of residues of biomass, what are you doing with these waste streams?
So the residues of biomass, which are not, from where we extract the carotenoids, they can again be used for animal feed. They can be used to make biogas, and they can be used to make fertilizer.
Okay, we are out of time. Thanks. Thank you for the presentation.
Thank you.
Thank you for the answers. And we move forward to Portugal. Lucas. Bom dia.
Hello. Hello.
Please start sharing and start presenting.
Just 1 second, please. Okay, help. Okay, are you seeing the presentation?
Yep.
Excellent. I should just go for it, Lucas. Okay, good morning, everyone. I'm Lucas, and we are part of Sally Solutions. Well, why isn't this moving? Okay, as previously mentioned, fresh water is running out. Water scarcity is a rising concern all throughout the world and is, of course, being worsened by climate change. By 2050, most of the Mediterranean countries will have high water stress. But as soon as 2025, it is thought that over half of human population could be facing some form of water stress. A prediction that is unfortunately already being widely observed and could even lead into geopolitical conflicts. So how do we solve this problem? Well, it's ironic that there is a water shortage in a planet that is 70% covered in water. Of course, it is mostly salt water. But due to nowadays technology, it is possible to just remove the salt from the water. So seawater desalination has been a major solution to water scarcity and is witnessing an increasing popularity, particularly in the arid and semi-arid countries. Saudi Arabia, as an example, is currently the largest producer of seawater desalination volume, reaching over 200 million cubic waters of fresh water per day. In the Iberian Peninsula alone, there are already 700 desalination facilities with a production of over 4.5 million cubic meters of fresh water per day. However, if we have fresh water on one hand, then on the other hand, it produces extremely large volumes of brine, a hypersaline byproduct, which can be 2 to 3 times saltier than the seawater. There are currently several methodologies for brine treatment, including deep well injection and evaporation ponds. But they are also quite expensive and energy intensive. It is estimated that this brine, the brine treatment, costs around 5 to 35% of total expenses of the desalination process. It is, of course, much easier to simply discard this brine directly into the ocean, which, of course, will cause significant environmental damage in the already deteriorated marine environment. That is a growing problem that is expected to worsen, especially when considering that for each liter of fresh water produced, 1.5 liters of brine is formed. And this is where our company comes in. In essence, by using a biocircular economy approach, our plan consists of a sequential phytoremediation process of this brine by reusing it as a culture media to produce two salt-tolerant or halophyte species, Dumniella salina microalgae and Salicornia hermosissima. These two species will be integrated into photobioreactors and into hydroponic systems, leading to the gradual removal of the salts from the brine, while also promoting the growth of Salicornia and the microalgae biomass, two high valuable products. This means that the desalinated brine will then be safely discharged back to the ocean, or we can even use it for other purposes.
But you may ask, why these two species? In essence, Salicornia is an edible plant. It's usually consumed as a legume and has been experiencing a recent surge in popularity, not only because of its characteristic flavor, we all know it if you try it, and its striking salty taste, which makes sense, it extracts the salt, but also because on the one hand, it has recently been acknowledged as a potential fuel crop because of the high oil content of its seeds, but also, of course, it can be dried and ground into a powder for the creation of what is called the green salt, which is essentially a spice used for flavoring, which has a reduced sodium content, and so it is particularly adequate for people suffering from hypertension. Microalgae, on the other hand, are starting to be known as the green gold, because they are extremely easy to grow and are a major raw material for a wide variety of industries, from cosmetics to food, biofuels, and of course the extraction and refining of high-value compounds with important pharmacological properties. In terms of market data, the microalgae market is expected to grow steadily in the coming years at an 8.5% annual growth rate, and it is expected to reach over 1.25 million euro by 2030. Currently, the Dunaliella salina is valued at over 35 euro per kilogram of dry weight. Salicornia, as mentioned, is still a lesser known legume, but it is indeed growing in popularity and it has plenty of room to grow. Currently, it is marketed at over 30 euro per kilogram of fresh weight, or dried. The green salt is marketed at over 350 euro per kilogram, which is not unusual for what is essentially a spice. In terms of our core business, so our plan is to use the desalination services themselves, of course, but mostly finance our entire operation with the production of these three high-value commodities. The microalgae would be attempting to target the processing facilities themselves directly through a B2B strategy, while the fresh Salicornia and green salt could target both gourmet restaurants and hotels, and of course the everyday consumer through both a B2B and B2C strategy. Even though we do plan on charging for our desalination services, for our phytoremediation services, we expect it to be a minor portion of our income. In terms of financial prospects, we envision a relatively small proof of concept prototype, which would require an investment of 20,000 euro, which would allow for the testing and optimization of our process, which would then be scaled up to a larger facility, over 2 hectares, which would require, of course, a much larger investment. We are expecting 1.3 million euro, but would allow for the annual production of 40 tons of microalgae and 120 tons of Salicornia, which, assuming a 5-year consolidation period of the production itself, and of course a best case scenario of the market insertion, could allow us for over 7 million euro in profit every year, which indeed would allow us to reach a break-even point within the first year of full operation. Thank you so much for your attention. This is the team that brought this concept to life, and we'll be gladly answering your questions.
Wow, that was quick. Thank you.
Yeah.
Okay, we are open for questioning. Manfred.
Yeah, thank you for this clear presentation. I understand the product. I'm waiting for it, but I didn't get why you are focusing on brine, because these microalgae and the plants, the salt-tolerant plants, grow on any seawater.
I'm not sure I understood your question. Could you repeat the last part, please?
They grow in seawater.
Yeah.
But
Yes.
why do you use this brine from the desalination plants?
It's mainly because we can reuse something that would be discharged and probably harmful for the maritime environment and for the fishes or whatever. And all
so there is no benefit from it.
Sorry?
there is no benefit from using these residual water.
The benefit is not having to release it to the environment. The objective is to tackle this issue.
We can reuse something that would be previously something harmful for the environment. So we can recycle it to produce something that's actually valuable.
And besides, the higher the salt concentration, theoretically, the faster the plant would uptake it, if, of course, it doesn't affect the growth rate of the plant itself. If the plant grows at the same rate, but the salt content is higher, it would also remove more salt quicker. One of our greatest challenges.
Did you test that by any means?
Unfortunately not. It's mostly theoretical.